Okay, so let's discuss a few questions related with this conservation of energy. So we have these three different tracks. So you have this slope, your mass starts from a higher point, it accelerates downwards. So there are three possible routes. Either it goes from 1 or through 2 or through 3. So the question is, what is the final speed at the finish if it takes track 1, track 2, and track 3? There is no friction. Well, you can send your answers as A, B, C, D. If it starts from the same point, goes through 1 and reaches the finish, what is it? Is it its velocity speed? Is it larger or smaller than if it starts from here and goes straight? If you start your mass from here and it goes through this path 1, these are three different paths. So suppose I have this surface, a mass just slides down and reaches the finish. This is one possibility. Or I put some obstacle on the path and I put a bump here. It starts accelerating, goes above the bump, then down and reaches the finish. Or there is I dig a hole, it goes down the hole and then up and reaches the finish. So how does its speed change depending on which way it goes? This is the phone number. There is currently just one person who has answered. Sorunun Türkçesi. Okay, so now oops, what happened? How many answers? Okay. 27 answers, most of them D. Sorunun Türkçesi. Buradan bir kütleyi bırakıyorsunuz. Eğimden aşağı kayıyor. Aşağı vardığında 3 ayrı yoldan gidebilir. Ya bir tümseyin üzerine çıkıp inebilir, ya bir çukurun içine girip çıkabilir, ya da dümdüz devam eder. Bu 3 yolda sona ulaştığındaki hızı nedir? Finish çizgisine ulaştığında hangisi daha hızlı, hangisi daha hızlıdır, yavaştır ya da hepsi aynı mıdır? Neyse, süreniz bitmiş ya da bir aksaklık oldu. Epey bir kişi D demiş cevap verenlerden, 27 kişiden. Yani süre dolmuş sanırım. Doğru cevap D. Şimdi the correct answer is D. All of them reach the finish with the same speed. This is one of the beauty of energy conservation. You see, if you imagine how the object moves, it can be quite complicated depending on the path. At this point, everywhere it has its weight. At this point, there is a normal force in that direction. If it's taking the above track, there is a normal force in this direction, another normal force perpendicular. At this point, there is a normal force in that direction. You have all these complicated normal forces, but nevertheless, When it reaches here, independent of how it went from this point to the final point, the speed will be the same. Because they are all reaching the final point where they have the same potential energy. Initially, they all have the same potential and kinetic energy. From the conservation of mechanical energy, it should have the same mechanical energy when it reaches the final point. Since the potential energy only depends on the final point, they all come to the same point. So the kinetic energy has to be the same. Now there's a more complicated question. The same diagram, the problem is almost the same. They both start from the same point. There are all the three options. They reach the finish point. But this time what I am asking is, which one takes the shortest time to reach the end point? If it goes through 1 or through 2 or through 3, will it have the shortest time? Buradan başladı. Finish çizgisine ulaşması için, en kısa zamanda ulaşabilmesi için hangi yoldan gitmesi lazım? Let me start the voting. So why do you think it is 2? Why did you think it was 2? Okay, there was one answer. Any objections to that answer, or does everybody agree with that answer? Your friend is saying that the speed was the same independent of which path it took. So the shortest distance was 2, so it takes the least time. Faster. But still, what about that? His explanation? Yes? So what if, for example, I had the path was like this? Would it still be 3? The answer would still be 3. No or yes? You said no and then you said yes. Okay, the problem with your answer is that they will reach this point with the same speed. We are not making any claim that it will have they will have the same speed throughout the path. As your friend pointed out, while they are moving here, if they are moving here, they will have a larger speed than if they are moving here. And they will be even slower if they are moving on the top of the hill. Here they have a larger potential energy, so the kinetic energy is smaller. Here they have the least potential energy, so the kinetic energy is the largest as they go here. So here they go faster, but the problem is they also go a longer distance. So how can you, okay, they go faster, which means they will reach the finish earlier, but they also take a longer path. It might mean that they will take a longer time to go to the end. How can you be sure that still number 3 will reach the finish first, independent of this size over here? So you are saying that if this path is shorter, then this might be late. No? That's not the correct answer. Well, let's look at, okay, one thing is the speed. We know that here it has a larger speed than over there. Okay, the other thing is okay, so we know that its potential energy here is decreasing. Okay, that is so that the kinetic energy should be increasing. That is from the point of view of the energy. What about its acceleration? What can you say about its acceleration? What causes the acceleration? There's a gravitational force, great. But the gravity causes them accelerate downward only, not in the horizontal direction. But this object is also accelerating in the horizontal direction because of the normal force. So let's just study the horizontal motion only, not the vertical one. Both objects reach here. They have some horizontal velocity. And they are both supposed to cover the same horizontal distance, because once they reach here, they have the same velocity, same speed, everything is the same. So the critical thing is this region. Let's just look at the horizontal speeds. Now, at this point, this is the direction of the normal force. It has both a vertical component and a horizontal component. So its horizontal velocity is decreasing because its horizontal acceleration is pointing in the opposite direction to its horizontal velocity. So when it throughout this region, it has a slower horizontal velocity, and then it moves with a slower horizontal velocity throughout this range. And then in this region, okay, it is accelerating. But if you just plot its horizontal speed, let's say call it x, as a function of time, let's say. Horizontal speed, it had a horizontal speed, it decreased, it went constant, and then it increased to the same final value. This is the horizontal speed as a function of time graph for an object that goes through path 1. Now for path 2, well, the horizontal speed is just constant. The normal force is vertical, the gravity is vertical. So it reached there with this velocity. So it will move with the same horizontal velocity. Well, of course, it will reach this final point at an earlier time. Let's call this T1. This is T2. Because remember, the area under this curve gives you the distance covered. This whole distance should be this horizontal distance. Now let's look at the third one. The normal force is in this direction. So its horizontal component of the velocity is increasing. It is covering a horizontal distance at a faster rate. And remember, the horizontal motion and vertical motion, they are independent motion. It doesn't, well, of course, this length is larger, but I don't care about that length. I'm only looking at the horizontal motion. And the horizontal distance for all these paths are the same. So this object will reach here earlier than the one that takes this path, and even earlier than the one taking this path. They will cover, this distance will be the same, whether short or long. That is why it will not depend on that. Now the third path will be this one. It will be the horizontal speed will increase, and then it will stay constant. And so to cover the same horizontal distance, and then it will decrease, it should take even a shorter time. This is T3. Yes, your question. Not really, because now we have the normal force also. What do you mean trajectory? Which ones? Up to this point, they have the same speeds, okay? This one is speeding up. Both its horizontal component and the vertical component are increasing. This one. Not really, if you only consider the horizontal displacement. As this one goes from this point to this point, the horizontal displacement is this one. But as this one is going from that point to this point, the horizontal displacement is the same. The vertical displacement is different, but the vertical displacement, I'm not worried about. I'm not interested in the vertical motion. I only would like to know the horizontal motion. I don't apply a force. The forces are already there. There is the gravitational force, which gives it an downward acceleration, plus the normal force, which causes it a vertical acceleration plus a horizontal acceleration. So there are forces, the weight and the normal force. The weight and the normal force, they both give a vertical acceleration, but I only consider the horizontal one. I can do that. I can separate the vertical motion from the horizontal motion. It's only the normal force which gives a horizontal acceleration. And the horizontal displacement of my object as I go from this point to this point, or this point, or this point, the horizontal displacements are always the same. Sure. It doesn't have such a large speed. If it has a small speed, it will follow this path smoothly. It will not be jumping. Okay, take a sheet of paper. You have 5 minutes, not more. That is your quiz. Now, I was planning to make that quiz, but I don't think that is fair. This one will be your quiz. That is something we had only studied now. You have two pulleys, M1, M2, frictionless massless strings. Draw the free body diagrams for mass M1 and M2 only. Sorry? That one is the quiz.